Let me tell you about a word that makes developers break out in a cold sweat. Refactoring. You know the feeling. That component that's grown into a monster. That database table that desperately needs restructuring. That code you wrote 6 months ago that you're now afraid to touch. And so you don't touch it. The technical debt piles up. The code base gets harder to work with. And everyone silently agrees to just work around the problems. But here's what I've discovered. Refactoring is only terrifying when you don't have the right guardrails. With the architecture we've been building in this series, refactoring becomes routine. Database schema changes? No problem. Splitting bloated components? Straightforward. And here's the bonus. The same architectural patterns that make refactoring safe also let you run multiple AI agents in parallel, working on different features simultaneously without conflicts. In this lesson, I'm going to show you exactly how it works. We're going to refactor a database schema, extract a complex component into smaller pieces, and set up parallel AI workflows, all without breaking a sweat. Let's dive in. Refactoring is one of the most valuable activities in software development. It's also one of the most feared. Teams put it off indefinitely. Technical debt accumulates. Code becomes harder to understand, harder to modify, harder to trust. The reason for this fear is simple. Without proper guardrails, refactoring is gambling. You change something here, and something breaks over there. You rename a function, and 5 tests fail in unexpected places. You improve one component, and 3 others stop working. This isn't irrational fear. It's learned experience from systems that lacked foundational discipline. Here's the truth that changes everything. Refactoring is only dangerous in code bases without guardrails. In systems with proper vertical slice architecture, comprehensive tests, and structured logging, refactoring becomes routine. Not because the risks disappear. The risks are managed. The blast radius is contained. The feedback is immediate. You know within seconds whether your change broke something, and you know exactly what broke. This lesson shows you how to refactor safely with AI assistance, and how the same architecture enables multiple developers or multiple AI agents to work in parallel without conflict. The patterns we've built throughout this series weren't just about building features. They were building a foundation that makes change safe. Vertical slice architecture isolates features from each other. Tests validate behavior automatically. Logging provides visibility into what actually happened. Type checking catches contract violations before runtime. These aren't luxuries. They're the infrastructure that transforms refactoring from a high-stakes gamble into a predictable engineering activity. When you have these guardrails, refactoring becomes something you do regularly, not something you dread. Let's explore 2 categories of refactoring that demonstrate these principles. First, we'll look at safe refactoring within a single feature. Changing database schemas, splitting components, renaming abstractions. The kind of changes that terrify teams without guardrails, but become routine with them. Second, we'll explore parallel work, how the same architecture that enables safe refactoring also enables multiple contributors, whether human developers or AI agents, to work on different features simultaneously without stepping on each other's code. Both capabilities emerge from the same foundational choices. Let's start with a concrete example. You have a products feature that stores product data in a single database table. The business now needs to separate product information from pricing information. 2 tables instead of 1. This is a schema change. In legacy codebases, schema changes are terrifying because they affect everything that touches the database. In a vertical slice architecture, the blast radius is contained to one feature directory. The products feature owns its schema. Other features don't query products tables directly. They call products APIs. This isolation is what makes the refactor manageable. Here's the structured prompt for a database schema refactor. Context specifies we're in the products feature, with SQL Alchemy models and Alembic migrations. Tests use PyTest with a test database. Task is to split the product model into product and product pricing, create the migration, and update the repository and service layers to use both models. Constraints keep us in the products feature directory. We maintain the existing API contracts. External callers should not notice any change. Validation runs the full test suite, checks types, and verifies the migration applies cleanly to a fresh database. The AI generates the refactoring in layers. First, it creates the new product pricing model alongside the existing product model. Second, it generates an Alembic migration that creates the new table and migrates existing price data. Third, it updates the repository to query both tables and join them when needed. Fourth, it modifies the service layer to handle the new structure while maintaining the same response format for existing endpoints. The external API doesn't change. Callers still get the same data. The internal structure is different, but the contract is preserved. Now, validation. We run the test suite. Every test that passed before the refactor must pass after. This is the critical constraint. Refactoring changes implementation, not behavior. If tests fail, either the refactor broke something or the tests were testing implementation details rather than behavior. Good tests survive refactors. If your tests constantly break during refactors, your tests are brittle. The tests we've built throughout this series test behavior through public interfaces. They don't care how the data is stored internally. They care that the API returns correct results. What about the migration itself? Schema changes need careful handling. The AI generates the migration, but we verify it manually. We check that data is preserved correctly. We run the migration on a copy of production data if available. We verify that rollback works. Migrations are one area where human judgment remains essential, even with AI assistance. The AI can write the migration code. You verify that the data transformation is correct. This is the partnership model. AI generates, human validates. Trust, but verify. The logging infrastructure proves its value during refactoring. When you enable debug logging and run your test suite, you see exactly what database queries execute. You can compare query patterns before and after the refactor. Are the same records retrieved? Are joins working correctly? Is the new structure producing identical results through a different path? This observability transforms debugging from guesswork into forensics. You're not wondering what happened, you're seeing what happened. That's the difference between hoping your refactor worked and knowing it worked. The same principles apply to front-end refactoring. Suppose you have a product card component that's grown too large. It handles display, editing, and deletion all in one file. You want to split it into smaller, focused components: product card display, product card editor, product card actions. The original product card becomes a composition of these pieces. This is a structural refactor. The external behavior stays identical. The internal organization improves. Tests that validate behavior from the outside should continue passing. Here's the front-end refactor prompt. Context specifies React with TypeScript, Vitest for testing, and the existing component structure. Task is to extract display logic into product card display, editing logic into product card editor, and action buttons into product card actions. The main product card component should compose these pieces. Constraints require maintaining all existing props and behavior. The component's public interface cannot change. Any component that renders product card should work identically after the refactor. Validation runs the existing test suite and verifies no visual regressions in Storybook. The AI generates the extraction. Each new component receives the props it needs from the parent. Product card display gets the product data and renders the read-only view. Product Card Editor receives product data plus update handlers. Product Card Actions gets the action callbacks for edit and delete. The parent product card manages state and passes appropriate props to each child. The component tree is deeper, but each piece is simpler and more testable. Responsibility is distributed across focused components rather than concentrated in one monolith. The tests validate that nothing changed from the user's perspective. Tests don't care that there are now 4 components instead of 1. They render product card, simulate user interactions, and verify the expected outcomes. If the tests pass, the refactor preserved behavior. You can now add tests for each extracted component individually, testing edge cases that were harder to isolate before. The refactor didn't just improve organization, it improved testability. That's the compounding benefit of good architecture. Each improvement enables further improvements. Now let's explore parallel work. In traditional monolithic architectures, multiple developers working simultaneously creates constant merge conflicts. Developer A changes a shared utility. Developer B also changes that utility. Both pull requests conflict. Time is wasted resolving merges. Code reviews become complicated. The velocity promised by adding developers never materializes. You've heard the phrase that adding people to a late project makes it later. This is largely because of architectural choices that create coupling. Vertical slice architecture changes this dynamic fundamentally. Each feature lives in its own directory. Feature A has its own models, services, routes, and tests. Feature B has its own models, services, routes, and tests. 2 developers working on different features rarely touch the same files. They work in parallel without coordination overhead. When they do share code, it's through well-defined interfaces in the shared directory, which changes infrequently by design. The architecture creates natural boundaries that enable independent work. This benefit extends directly to AI-assisted development. You can have one AI session working on the orders feature, while another works on the inventory feature. They operate in different directories. They run different test suites. They don't interfere with each other. As long as they follow the established patterns and don't modify shared code without coordination, their work can be merged independently. The same principle applies whether the parallel workers are multiple humans, multiple AI agents, or a combination. The architecture doesn't care who's writing the code. It cares that boundaries are respected. What about shared code? The shared directory contains utilities, types, and components used across multiple features. This is the coordination point. Changes to shared code can affect multiple features, so they require more careful handling. The rule is simple. Features import from shared, features never import from other features. Shared code changes infrequently because it represents stable abstractions. When shared code does need changes, those changes are explicit and intentional, not accidental side effects of feature work. Here's a practical workflow for parallel development. Developer A starts working on the product search feature. Developer B starts working on the orders export feature. Both work in their respective feature directories. Developer A finishes first and merges their PR. Developer B continues working. When Developer B finishes, they merge their PR. No conflicts because the work was isolated. Both developers ran their feature-specific tests. Both verified their changes didn't break the main test suite. The architecture made coordination unnecessary for independent work. The same workflow works with AI agents. You can run multiple Claude Code sessions in separate terminal windows, each working on a different feature. One session adds a product recommendation engine. Another session improves the checkout flow. As long as each session respects feature boundaries and doesn't modify shared code without explicit instruction, their work can be merged independently. This is how AI amplifies team velocity. Not by one AI doing everything faster, but by multiple AI sessions working in parallel on different concerns. What happens when conflicts do arise? First, recognize that the architecture minimizes conflicts, not eliminates them. Sometimes two developers need to modify the same shared utility. Sometimes a feature change requires updating an interface that other features depend on. The goal isn't zero conflicts. It's predictable, manageable conflicts that occur in well-defined places rather than scattered randomly throughout the codebase. When shared code needs modification, use a coordination protocol. First, create the interface change in a dedicated PR that touches only the shared directory. Get that reviewed and merged. Second, update features to use the new interface in separate PRs. This sequencing prevents conflicts. The shared code changes once in isolation. Features adapt to the change independently. Nobody is racing to modify the same files. The architectural boundary becomes a coordination mechanism. For AI sessions specifically, establish clear boundaries before starting parallel work. This session works on products. That session works on orders. Neither touches shared without explicit permission. If an AI session needs to modify shared code, stop that session. Handle the shared change manually or in a dedicated session. Then continue. This discipline prevents the scenario where two AI sessions both decide they need to add the same utility and create conflicting implementations. Clear boundaries make parallel AI work predictable. The CI pipeline serves as the final safety net. Every PR runs the full test suite. If two parallel changes somehow conflict in ways that weren't caught during development, the tests catch them before merge. Type checking catches interface mismatches. Linting catches style inconsistencies. The automated validation layer ensures that nothing reaches main branch that breaks the overall system. This isn't just a safety net for parallel work. It's the foundation that makes parallel work confident rather than anxious. Safe refactoring and parallel work are two sides of the same coin. Both emerge from the architectural choices we've made throughout this series. Vertical slices create natural boundaries. Tests validate behavior automatically. Logging provides visibility. Types enforce contracts. These foundations weren't arbitrary design decisions. They were investments that compound over time. Every feature you add following these patterns makes the next feature easier to add. Every refactor you complete safely makes the next refactor less scary. The system gets better with age rather than accumulating debt. This completes Module 4 of the Foundation series. You've learned the PIV discipline, from structured prompts to validated changes. You've applied it to back-end work, front-end work, and full-stack features. You've seen how the same architecture that enables individual productivity also enables team scalability. In the final module, we'll transform these patterns into reusable templates. You'll learn how to adapt these foundations to different technology stacks, how to integrate AI and agent infrastructure into your codebase, and how to maintain AI-optimized codebases over time. The journey from understanding to implementation to template is almost complete. Subscribe to ensure you don't miss what comes next. Let's recap what you just learned, because this is a lot of power in one lesson. First, safe refactoring. You saw how to split a database table, extract components, and restructure code with complete confidence. The secret? Vertical slice architecture contains the blast radius. Tests validate that behavior survives the change. Logging shows you exactly what happened. When you have these guardrails, refactoring stops being a gamble and becomes a routine engineering activity. Second, parallel work. You saw how the same architecture enables multiple developers or multiple AI agents to work simultaneously without stepping on each other. Each feature is isolated. Each has its own tests. The only coordination point is the shared directory, and that changes infrequently by design. This is how you actually scale a development team, human or AI. And here's the insight that ties it all together. These aren't two separate capabilities. They're two expressions of the same foundational discipline: vertical slices, comprehensive tests, clear boundaries. Every investment you make in this architecture pays dividends in multiple ways. Now, if you found this valuable, I need you to do three things. First, hit that subscribe button. Module 5 is coming, and it's where we turn all these patterns into reusable templates you can clone and customize. You don't want to miss that. Second, smash that like button. It tells the algorithm that developers want this kind of deep, practical content about AI-assisted development. And third, hit that notification bell so you know the moment the next video drops. You've made it through Module 4. You now understand how to build full-stack features with AI, how to refactor safely, and how to scale your development capacity with parallel work. That's a serious skill set. Go put it to work, and I'll see you in the next module.